Okay, hopefully this is now live. Ba-dum. Things going a little slow here on the connection. Hopefully this is going to work okay. So, some familiar faces. ONG, Crypto Hippie, thank you very much. W. Bullmans, Neek, good to see you all again. Stuart XRP, hello. Aramis87, Melanie Chapman, hello all. Yes, Aramis, a Python console. I will be doing some stuff with Python as part of this. So, slight spoiler there. Not really a spoiler, I suppose. But can you all hear me okay? Hopefully this is going okay, and hopefully the stream is not too choppy. Like I said, YouTube seems to be thinking that it's thinking it's good now. Okay, hopefully we're okay. So if someone can just let me know that you can hear me all okay on the stream, that'll be good. I'm always a little nervous that I'm going to start and go talking for ages and realise that nobody can hear anything I'm saying. No doubt you'd all jump up and down and wave your arms around. I will also just say that I'm afraid I've got a little bit of a cold, so I've got my Lemsip with me, and hopefully I won't be sneezing and coughing too much. So, Aramis, Jeremy, sorry I didn't recognise you there, Jeremy. Great, thank you for joining on. So, great, okay. Well, I guess I'll get started. So this episode came about. I know a number of you are doing a online course, a MOOC, a massively online course, open course, with the University of Nicosia, I think it's pronounced. Their MSc Digital on digital currencies, which is great. I was hoping to actually do it myself as well. Unfortunately, didn't have a chance to. Nordican, who's on there, one of the XRP community members, was talking as well with Jeremy about some of the coursework, and was talking about some of the stuff that happened this week about hashes and signatures and encodings. So I thought we could cover that today and talk about some of the elements that are kind of the basic building blocks of not only cryptocurrencies but a lot of computing, a lot of messaging on computers, a lot of how computers work. So we're going to go right back to kind of the basics of how computers store information, store numbers, how they count, how they represent information, and kind of build up from there. And hopefully that'll give a bit of an understanding as to maybe where these things come from. So to kind of set the scene, I think the coursework that was on the MOOC this week was to do with Bitcoin addresses. So how a Bitcoin public address is formed, and very similarly an XRP address and a lot of cryptocurrency addresses are formed in a very similar way. So I'm going to sort of work towards explaining that. Like I said, I'm going to cover some of the background sort of bits and pieces as well. And yes, thank you ONG and Crypto Hippie. Yes, subscribe and like is very helpful for me for knowing what people are enjoying on here, and also I get certain privileges with YouTube to be able to do things on the channel if enough people like it, which is good. So, like I said, right back to beginnings here. Let's see where we start. So, computers and memory and how they work. So in which each element just has two states, either a 0 or a 1. Now the reason for this being is going right back to the start of computers, in which computers were basically assembled from a series of switches. A switch can either be on or it can be off. And all computers build up from that basic premise. So your, Intel i7 processor or whatever has billions of transistors in. All it is lots and lots of very, very, very tiny switches. But in essence, all computers started from the notion of switches. So looking at things like punch cards, so these were originally developed at IBM with a big company that standardized them. Originally a company called the Tabulating and Recording Company, I believe it was they were called. They were called something else before them, but the Tabulating and Recording Company became IBM. And one of the things that they kind of pioneered was the use of punch cards. And the idea behind a punch card is it is a card, a piece of paper or a card, and it has holes that can be put in it. And these cards are fed into a punch card reader. And when a punch card reader, here, let's see here, punch card in the machine, you can kind of see here. This is a punch card that is being punched. So this is a punch that press down on the keys and it punches holes in. So this is an operator doing it. You can see they've got little thimbles on their fingers. Obviously, they do this for quite some time, so it's quite a manual process. But that will create a card, and that card has holes in it, and it could be fed back into a machine to be read, and the machine would detect where those holes are. And where there's a hole, it would be a 0, and where there's not a hole, it would be a 1, or vice versa. It doesn't really matter which way. But basically, those holes, or the absence of those holes, will represent whether or not there's a 1 or a 0 there. That's kind of where things sort of started. And then from there we got onto things like vacuum tube memory. So there's another one, there's things called mercury delay lines, there's all sorts of things, but most of these were basically ways in which you could represent a switch. And these tubes that were used here, these vacuum tubes, from some of the early computers, they were switches, and the great thing is they were a switch that could be switched on remotely. So you have two terminals and a third terminal, and when you put power onto that third terminal, it causes the switch to close and power can flow between the first two terminals, right? And so nowadays we have what are called transistors that do the same thing but much smaller, and we're now down to the case of these things, the tiny, tiny microscopic things on computer chips. And so a computer chip, when the integrated circuit, the IC came about, it was a single chip, a single wafer of silicon, and that had everything in. Along the way we go through things like core memory. So these were, if you look here, you see these wire wrapped memories here that we use. So these great big lattices of wires that represent memory. But all they were in the end was ones and zeros, right? So that's how memory was stored, and still is stored. That's how computers work, ones and zeros. So how do you represent information in ones and zeros? So 1 and 0 is 1 bit, and the kind of convention we've come up with is 8 bits together make a byte. So how much information can you store in 1 byte? Well, it is 2 to the power of 8. So if we go, like I mentioned, I've got a Python terminal here. So Python, I'm going to be doing some stuff in Python here. Python is a great programming language. You can go to python.org and you can download a Python interpreter. If you've got a macOS machine, you'll have Python on there. If a Linux machine, you probably already have Python on there. Windows, you can download it. Anything else, you can probably download it as well. Python's a fantastic programming language. It's used for all sorts of things. It's used for a lot in data science and a lot in web. But the great thing big is you can just type Python. It'll give you a prompt and you can start typing things. So if I type 1 + 1, it'll come back and say 2. So I can just start typing in equations or commands or functions, and it will just evaluate them there for me. So I asked the question, how many things can you store in 8 bits? And so the answer is 2 to the power of 8. So let's say represent power in Python, and the answer is 256. So we can store 256 different values. So we can count from 1 to 256, or 0 to 255, because computers normally start with 0 rather than 1 when they're counting. So 0 to 255, we would need 8 bits. So if you have 8 switches, imagine you just went and bought 8 switches from a hardware store and put them in a line, and with those 8 switches, there are 256 different combinations you could set those switches in, and that's how you could represent 256 characters. So that is what we call a byte. So most computers originally, they were, as time has progressed, they have become more powerful, and they have been able to address more and more information. So we had 8-bit microprocessors, and you'd still have some of those in some very small embedded systems will be 8-bit systems. Then came 16-bit, then came 32-bit. Most of your desktop computers now will be 64-bit, anyone's purchased at the moment. So your Windows, Mac PCs, even your mobile phones will all be 64-bit. They even have some 128-bit operations in. So what that means is they can count higher, right? A 8-bit computer could only reference 256 different locations in memory. So a 16-bit computer, if you doubled that, a 16-bit computer can go a lot higher. A 32-bit computer can go higher than that. 64-bit, as you can see, it gets really quite large. So a 64-bit computer can address a lot more memory, and then 128 even further. So why are we talking about this? Why am I talking about this when we're talking about encodings? So each character that you see on the screen, any character that I type on a screen is represented generally as a byte. Now, a long time ago, there was a standard in the US called ASCII, the American Standard for Computer Information Interchange, I think it stands for, and they determined which numbers would be used internally to represent a character. So if I type an A on a computer, it's stored internally as a number. So the number it's stored at, if I can remember in Python which way around is 97. So an A is 97. And then actually quite logically, a B, 98, C, be 99. Okay? So as it goes up. So Stuart's just asked, is there a limit to a bit? A bit is still just 2 states, on and off. There is, and this is going into some further stuff, there was some experiments with having what are called ternary logic, in which a bit can have 3 states, which obviously can represent a lot more information. And actually, in a lot of cases, that was used to represent not just kind of yes or no, but yes, no, and I don't know. So it actually came some interesting logic stuff that you could do there. And then the big thing with quantum computers is that there's almost potentially an infinite number of states. So that's why it can be a lot more. So Crypto Hippie has asked, quick question, why does mine give the L at the end? That's probably because it's giving you a really long number, and the L means it's a long number. So again, in programming languages, you would have different variable types. So a regular integer might be 32 bits. What's called a long integer would be 64 bits. Now I'm using Python 3. You are possibly using Python 2. So it might say at the top Python 2.7 or something like that at the top. Python 3 it's a later version and works slightly different to Python 2. So it may say that by default, or it might be depending upon whether you're on a 32 or 64-bit computer. Like I said, most new computers now are 64-bit, but some programs will still be running in 32-bit mode. So again, why are we talking about this? We're talking about this because we're trying to work out how computers represent information. And so, as I said, there was a standard that was drawn up called the ASCII standard. And actually, if I just quit Python here quickly, and if I type man ASCII, so man is for manual page on Unix or on Mac OS, and if I type man ASCII, it'll bring up a page that gives me the ASCII character set. So if we look at, if I actually go down to the decimal set, just to start with to be easier. This tells you what number all of these different characters are. Now some of these characters, so 0, 1, 2 here, null, SOH, STX, are what are called control characters. You can't see them on the screen. So the ones that we can see, the printable ones, are the ones that we're kind of used to, A, B, C, D, etc., and numbers. And also you see here we're only going to the first 127. That's because 127 is 7 bits. When ASCII was first created, there was only, most computers only used 7 bits, and they used what they called the 8th bit for what was called the parity bit. And remember that, because we'll probably come back to that when we talk about checksums in a little bit. But in short, the parity bit was used to detect any errors in the previous 7 bits. So they had 128 characters, 0 to 127, and that's where our numbers are and how they're represented. So if I go back to Python, but as you know, there's only a certain number that we can actually kind of see. So if I was to try and represent an arbitrary number of bytes and present it to you for you to be able to see, that would actually be quite difficult, because as you saw on that man page, only a certain number of those bytes will map to visible characters. So if I want to represent the number 97, then that's easy because that's an A, or 98, that's a B. But if I wanted to represent a number that wasn't there, so you can go the other way around here. So if I go CHR, I think it's CHR, yeah, CHR 97 will give me an A. That tells me what character is at 97. Say I did 20. Well, that's something quite weird. So Python has helpfully put this /x on a number, and that means that I can't print it. So I'm just going to tell you what it is in hexadecimal. So that comes on to a good question. What is hexadecimal? So we talked about binary. That's what's called base 2. That is, there's 2 states, and everything's a 0 or a 1. And you can convert from binary to decimal. Decimal is the number system that we normally use. There's numbers 0 to 9, and we can put those together, and we can count up in those. Computers generally, internally, like I said, use binary, but there's also another representation called hexadecimal. Now remember I said there's 256 bits in a byte. So there's 8 bits in a byte. So there's 256 representations we could store in 1 byte. So another way of displaying it is actually by using what's called hexadecimal, which is base 16. So we have the numbers 0 to 9. Well, imagine if we had other numbers as well. Well, we can't really have other numbers. So instead what we do, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we actually start using some of the letters. A, B, C, D, E, F. So that gives us 16 characters. If I ask for the length of that, it's 16. So those 16 characters can be used. 16 times 16 is again 256. Right? So these characters I can use to represent something. So that X14, what it's actually saying is it's 14 in hexadecimal, which is the equivalent of 20 there. So this may be a little bit unclear, but I'll try and bring it back in a second. So CHR 97 is A. In fact, I can represent 97. I can ask it to, if I can remember which way around to do this. I can ask Python. So 97 is 61 in hexadecimal. So I can actually say /x61. Oh, maybe I meant it like that. Oh, or just like that. X61, yeah. So X61 is A. So 61 is the hexadecimal of 97. So the nice thing about hexadecimal is we can represent all 256 positions in a byte using the numerals and the letters 0 to F. So if I was trying to represent an arbitrary byte to you, I would have to tell you what it is in decimal or in hexadecimal. And hexadecimal is just a little bit more compact, and it takes up 2 characters, and rather than decimal, which would take up 3. So it would be the let's see here, the ordinal of Z is 122 in decimal, but in hexadecimal it's 7A. So it's a little more compact when you're representing something because it's 2 characters rather than 3 characters. And so you can take any set of bytes and represent them as hexadecimal. So let's try and bring this back to what we were talking about addresses and hashes and things like that. With Bitcoin and XRP and a lot of other cryptocurrencies, you have a secret key and you have a public key or a public address, and those are related to each other. So they're related by the fact that you can derive the public key from the secret key, but you can't go back again. So there's a mathematical function called a hash, which goes one way but doesn't go back the other way. If you remember, I described it once before about saying that there's certain mathematical functions that are easy to go one way but not, you can't go back the other way. So the analogy I gave at the time, I think, was a coffee, and I said, if I ask you to put sugar in a coffee, that's easy to do, and I can taste the coffee and I can tell it's got sugar in it. But if I ask you to take the sugar out of the coffee, that's near impossible. Certainly not without a chemistry lab and a lot of work, right? So you can go one way, but you can't go back the other way. So that's what a hash function is. And I'm going to show you some examples of a hash function, and they will take a arbitrary series of bytes and they will turn it into, they will create a representation of that, a hash of that, such that if I change any one of the original bytes, you'll see that change in the hash. So let's demonstrate that, be a little bit easier here. So if I say here import hash lib, and there's a number of different hash functions, and so, but if I say I create a string, I'm going to call it hello. So S is hello, right? Now I can say hashlib dot SHA-256, and that's one of the hashes that's used in Bitcoin. It may be used in the XRP ledger, but I think they use a different hash function. Different hash functions have different qualities, and some of the early hash functions were, like I said, you can't go the reverse direction, but some of the early hashes they found weaknesses in. So there's one called MD4 and then MD5, and those have all been deemed to be too weak now, and so we're now on to SHA-256, SHA-512, and some more modern ones here. But I can say hashlib SHA-256, and I can pass in S. Sorry, this is Python 3. So what I've actually got to say is I've actually got to say S is some bytes specifically by putting a little B there. And so now I can say that, and it gives me back what's called this hash object. Now what I want to do is I want to get back what's called the hash digest of that. So if I do that, it gives me this string. Now that string is, if I try to read that out to you or type that in, that would be a pain, because that's actually a bunch of bytes, and you can see the /x blah blah where Python has helpfully tried to represent it, because there's a bunch of bytes there that it just can't display on the screen because you wouldn't see them, because we don't have a representation for them to show on the screen. Remember, of the 256 bytes, if you think how many are if we look at alpha num, oh, I can't remember what the ASCII letters. Right, so we've got the alphabet, and then we've got digits there. So the length of that is 62. So we could only easily represent 62 out of the 256 characters. Okay, we could add some punctuation, dots and dashes and things, but we're soon going to run out of things to actually display on the screen for those other characters. So what we can do is we can actually convert that into hexadecimal. So that command I gave before that gave us this digest here, instead I can actually say hex digest, and it'll give it to me in hexadecimal. Now this is starting to look a little bit closer to a Bitcoin address or a Ripple address, right? It's a similar sort of thing you've probably seen before, long string of numbers and letters, and all the letters are between A and F. That's because it's hexadecimal there for that. Now actually we don't use hexadecimal, and in fact, sorry, I was slightly wrong there, because Bitcoin and Ripple addresses will probably have other letters in, because they actually use a slightly different encoding. So this is a hash. Okay, I'll get onto encodings in a minute. So this is a hash. I've taken that string, our string hello, and I've taken a hash of it, and I get that, right? Now, the beauty of a hash is whenever I call this on that same thing, I will get the same result back. If ever I give it hello and call hex digest on it, I'll get the same thing back. On my computer, on your computer, on any other computer that has the SHA-256 hash algorithm on it, then I can call this and you'll get exactly, you'll get the same thing. But if I make a slight change to that, so if I actually say S is hello 1, and I take a hash of it, I get a totally different hash. If you see, it's not just one small change, it's completely different. And that's one of the functions of a good hash, is that a very small change will make a massive difference. And it's, hashes can be applied to huge, great big strings of work, and you'll get just that one fixed same size hash. So I could take an entire, an entire book, and I could take the hash of that, and if I go in and change one character in that book, just a single character in it, you'll get a different hash. So this is how digital signatures are done. If I take a hash of something, a document, say I create a legal document, a contract, I then take a hash of it. If I then give that legal document to somebody else, if they make a slight change to that, then the hash will change and it'll be immediately obvious. Now, W. Boomans has pointed out a thing called hash collisions. So a hash collision is where there is the case in which two different inputs will give the same output, right? Now that is possible, because if you think we're reducing an input down to a much smaller output, so there must then be multiple inputs that could give the same output. But they're very rare, and they're very difficult to predict. It's very difficult to say, okay, what other string would give me the same hash out again? So I've got this legal contract. If I want to change something in there without changing the hash, it'd be near impossible for me to work out what little change I can make such that it reflects that hash. And the reality is, if it's something like a legal contract, if I suddenly have to make vast amounts of changes in order to get the hash to match, you'd probably notice, because it wouldn't look like a legal contract by the end of it. The changes I'd have to make would be so extreme. Now, there's some hash functions that are very easy to get hash collisions on. Like I said, those are not deemed secure now, but some of the newer ones, things like hash 256, hash 512, are a lot more secure. So it's a lot harder to do that. And this is actually what Bitcoin mining is doing behind the scenes. Bitcoin mining is doing this hash operation, and actually the what's called the hash cache, that's the puzzle that Bitcoin miners try to solve, is trying to say, what string can I hash that will give me a hash that starts with a number of zeros? And so you've got to keep trying different inputs until you find one that gives you an output that has a certain number of zeros at the start, and that's how you kind of win the Bitcoin mining kind of race that's going on, and it's your miner that gets to assemble the next block for the next 10 minutes or so, until the next block is found, which is roughly about 10 minutes. So, like I said, a hash is only one way, and a small change in the input reflects a large change in the output, right? An encoding is different. An encoding can go both directions. So this is our hash here, and I'm going to I'm gonna call this I'll just call it hash there, right? So hash, that's that value there. Now I can encode that, and Bitcoin uses encoding called base 58. So I can import base 58. It's a module. If you're doing this at home on Python, you'll have to install it with a command called pip. If you type pip install base 58, it will install it for you. So import base 58, and I can then type base 58 dot b58 encode hash, and that encodes it. Now, as you've seen, we've moved away from just the hexadecimal numbers, but actually one of the things with base 58 is that it removes some of the confusing letters. So I's and ones, or capital I and a 1, and a 0 and an O are missing, so that it's actually easier to kind of type this out without getting it confused. And you can go both directions. So if I take that output and I'll call that B58 hash. So here we have with B58 hash is that, and I can then actually say base 58 dot B58 decode B58 hash, and I should get back the original value. So that should be the same as hash down. I can even ask Python to tell me, does that equal hash? Oh, actually it doesn't, because one's a byte and one's a string. I think if I do this, I'm going slightly off track here. Sorry about this. There we go. Right. I've had to encode that through a thing with Python. The way in which Python 3 treats characters. As I said before, there was a standard called ASCII, and it was used to represent the characters A to Z, 0 to 9, etc. The problem being is the world is a bigger place, and there are many more characters than there are just A to Z. So, countries like Norway will have the A and E conjoined, which is not represented in ASCII, and you'll have even things like you go to China and Japan, and you have glyphs in the alphabet that are totally different. So there was a standard called Unicode, which instead of using the first 127 characters, which ASCII did, Unicode uses something like 16 million, I think it is, and includes all things like emojis. That's why we have emojis now, because we now effectively have a character set that is richer than just A to Z, and it can include all the kanji, it can include Arabic text, it can include Hebrew text, Cyrillic alphabets, and it can include your flaming poo emoji or whatever it is you want to have in there. So that's kind of all included in there. But the point of this is an encoding can go backwards as well. So you can go forwards and you can go backwards with an encoding, but you can only go forwards with a hash. You can't go back again. So you have your secret key in Bitcoin or XRP. You have your secret key, and then they take a hash of that, and that becomes your private key. So imagine that your secret key was 1, 2, 3, 4, 5, 6, and then your public key would be hashlib.sha256 of secret digest, and that all passed into base 58.b58 encode. So we're taking the secret, we're using the SHA-256 hash, we're getting the digest of that, which is the output of the hash basically, and then we're encoding that with base 58, and that should, if that works, Unicode must be encoded before hashing. Oh yes, it needs to be bytes again, sorry, my mistake here. So our secret is, just put a B there, indicates it's bytes. So that's our secret, and then public, and there we go. So public, we can see, there we go, that's our public address, right? Now we can't go back from that public address to the secret address. You can go forward from the secret to the public, but you can't go back again, and that's a key part of the security, because remember, the secret address is the one that you hold. The secret key is your private key. You hold that, close. You don't let anybody else see that, and that is the bit that allows you to say, you really own that particular wallet. Right, I'm glossing over a few details here about public and private key encryption. I did talk a little bit about that before, and how prime numbers are used to create those, the public and private key encryption. So look back on the channel if you want to see that. Here we go. Here's how I take a secret key, and we can get a public key. And like I said, you can run that however many times as you want, and you'll always get the same public key back. And again, you could run that on any other computer, and you would get the same result. But if I gave you that public address, there's no way from there that you can infer that my secret was 1, 2, 3, 4, 5, 6. Okay. So that's your public key. Now again, what if you go typing that in and you make a mistake? Right? You don't want to have a situation where you put your public address in to you're going to transfer some funds on Bitcoin or XRP, and somebody says, "Well, give me your wallet address, and I'll transfer you some XRP or some Bitcoin." So sure, yeah, here's my wallet address. You go put it in, you type it in, or maybe you copy and paste it, and you miss a character off, or you do something strange, and it goes slightly wrong. You don't want to have it that it's then going to send your funds to some wallet that doesn't exist, or someone else's wallet, because those funds would then be irretrievable. You would accidentally send them off to somewhere else, and you wouldn't get them back again. So you want some way to detect whether or not you've typed that in correctly. And again, we can use a hash for that, and we create what's called a checksum. So if we take our public, we've got our public key, our public address. Now if we take a hash of that, so say I take a hash, so I say again hashlib.sha256 of public .hex digest, we'll just use hex digest for now. That gives us the hash of that. Now I could take just the last 4 digits of that. So in Python, I can ask Python to give me the last, from the last 4 digits, this is what's called a range operator here, and I can say from the last 4 digits up until the end. And that gives me those last 4 digits, BEE6. So I can call that my checksum, right? So checksum is BEE6. So what I can actually say is my public key is actually that. I take the public key and I add the checksum. And again, I can't because I've got that Right, I've had to encode it so it knows how to turn that into bytes. But as you can see, you'll see this here, this byte string. We've got our original public key. Then we've got those last 4 digits, so they're the checksum. Now anybody can take this and take that first bit, and they can you know, whatever, they can run it, copy it, run it through, and say, okay, we're going to put it back through a you know, the hex digest again. Oh, didn't mean to assign that the hash, so I just meant checksum, just meant to run it there, and you'll get that BEE6 out. Now, if I had slightly screwed that address up, so say what I actually sent to you, I said that, you know, my public key was actually, so public key was that. Right, well, let's just change it here. Let's just say I got this slightly wrong, and I somehow typed it in and I got the Y and the 8 the wrong way round, because I was reading them out and I got them wrong, or I copied and pasted it and I lost a bit off the end. I get a totally different last 4 digits there. So I would check that against the end of the key that you gave me, and I would say, well, BEE6 is not the same as 3C28. So something's gone wrong there, right? The checksum has failed. That means I've got a mistake somewhere in there. So I can immediately reject that and say, no, you've got that address wrong, before I've even sent the funds. This can be done in your wallet software before anything even happens, because it knows that there's a checksum on the end. And sure enough, on XRP, you'll see here pretty much what I've been talking about. We have a secret key here, and there's this public key derivation that happens to get the public key, and they take the SHA-256 of that gives you the account ID. There's a reason, for some reason they use SHA-256 sort of twice on there, but then they take a checksum. Oh, the checksum's probably created by using the SHA-256. That gives you the checksum. So you take the account ID, you run SHA-256 twice on it, and take the last 4 bytes. That's your checksum. You add that onto the end, and there we go, base 58 again. You base 58 encode both of them. You get an address that is 20 bytes long with a 4-byte checksum on the end. And on Ripple, they put an R on the front, right? Just so you know that it's a public address, as opposed to an S for the secret key and an N to denote the key of a node or a server. Similarly, in Bitcoin, I think they put a 1 on the start or a 7 on the start, I think, depending on 3, depending upon which key format it is, and what it represents. So they have a similar kind of thing in which they take a public key. There's a checksum there. They use a hash called hash 160 instead, and you know, again, you come out with a base 58 encoded address. So this is the one here from the mainnet. Here we go. So we take the public key, hash 160, do a checksum, base 58, and that's what we get at the end there, right? So similar to an XRP address as well. So hopefully that I've managed to explain that. Hashes, using them as signatures and encodings and checksums. So to recap, a hash, you can only go one direction with a hash. So you use a hash to derive the public key from the secret key, because that means you can't go back from the public key back to the secret key. You can take a hash of a document, so you can then see whether something has changed. So you can use that as part of a digital signature. You can take a hash, and this is used in blockchains. So each block is, you take a hash of the previous block and you include it into the header, and then the next block takes a hash of that, includes it into its header, and the next block takes a hash that includes it into its header, and so it's the same the same format. So the XRP ledger header format on there, has got a hash. They use it's called SHA-512 just for performance reasons. In modern computers, it's actually quicker to do a 512-bit operation and then take the half of it than it is to do a 256-bit operation, just because modern computers are more optimized for some of these larger operations. So there was an image somewhere that showed this. Yes. Here we go. Ledger format. And take the input hash function on there. It shows you, yeah, each transaction ID there'll be a hash. Oh, that's an account one actually. Header format, transaction hash. That's the hash of the transaction. So again, if somebody were to manipulate the transaction in any way, the hash would then be invalid, and that's kind of how blockchains work, because they store the hash of the previous one and the next one, the hash of the previous one and that and the next one. So if you made any change, it would invalidate all the subsequent ones and be easily detected. And so encodings are just different ways of representing data. So you can base 58 encode it. There's a very popular encoding called base 64 that's used a lot in email, because original email systems were only able to transmit in 7-bit due to original limitations. So any kind of images that were attached were first base 64 encoded and then attached to an email. And if you actually manage to look at the source of an email, you'll see a whole bunch of stuff. You'll see it normally says base 64, and then a whole bunch of stuff there that represents the image as a way of transmitting it. And both Bitcoin and XRP use base 58, which is just a similar representation, but it removes some of the confusing characters so you don't accidentally mistype them. And then a checksum is a way of checking that all the others are valid. As I mentioned at the start, the reason why a lot of early computers used 7 bits for data was that 8th bit was a parity bit. So what you would do is you would take the data and you would see whether it's odd or even, and if it was even, you would add a 1 on the end to make it odd on the last bit, and then that would mean that you'd be able to detect if it had changed. Obviously it only works in half the scenarios, but it allows you to detect to some degree whether things are invalid, so whether the memory has stopped working or is being corrupted. And in the early days, that was obviously a very strong probability that something would stop working or that the memory would become corrupt, because it was literally a rat's nest of wires and mercury whizzing around tubes and things like that, so it could quite often go wrong, and so you needed a way to represent that. Checksums are also used in all sorts of other things, even things like your UPC barcodes. So the barcodes that are scanned on shopping goods, they often have a checksum at the end as well to make sure that the scanning has worked correctly. So they'll have a checksum on the end just to prove that you got it right, or the scanner got it right, it didn't misread it. So covered quite a bit there. Hopefully people are still with me. Hopefully that was useful and interesting. If people have any questions, then yeah, feel free to ask them now. Otherwise I will start wrapping up, because we're almost up to the hour. But if anybody has any questions, then feel free to ask them now. No? Okay. Brilliant. Well, thank you very much, everybody. If anybody does have any further questions or thinks of anything, then feel free to ask them in the comments or grab me on Twitter, and I'll chat to you then. So otherwise, thank you very much. Good night.